This is Lecture 1 for Module 5, Electric Current, in the book Problem-Solving Guide for Electromagnetism and Optics. Electric current is the flow rate of electric charge. We're only going to consider DC, direct current, current that flows only in one direction. I make that distinction because in your house, the current is AC. The plugs on the wall is alternating current because it's easy to transport over long distances. If you have long power lines, AC is much easier to transport without loss. So the symbol for electric current is capital I. International system of units are coulombs per second, and this is an amp. Coulomb per second is an ampere. To really understand what flow rate is, let's focus on something that you might already be a little bit familiar with, the steady flow of water in a pipe. So here's our pipe. It's got a cross-sectional area A, the size of the pipe. Cross-sectional area A. The volume flow rate through the pipe is volume per time. And the volume per time is the area times the length that comes out. So let's put an X on here. And we can imagine a plunger here that's going to push all of this out in time t. The distance traveled over the time, we call that the speed of the water through the pipe. So the flow rate of water through a pipe is the area of the pipe multiplied by how fast the water is moving through the pipe. This basic concept applies to the flow of charge, but there are some differences. The atoms themselves don't flow in a wire, right? The copper atoms just sit there. The electrons, the free electrons, flow around the atoms. And instead of being volume per time, it's coulombs per time. So it's not even electrons per time, it's coulombs per time. If we know the flow rate of electrons, it's easy to get the current, the flow rate of charge, because we know how much charge is on an electron. One electron has 1.6 times 10 to the minus 19th coulombs, so it's easy to convert from electrons per second to coulombs per second. And that's the current, coulombs per second. So we're going to ignore everything else in the wire. Just the free electrons. The electrons that contribute to the current, the electrons that can flow over long distances. So we're concerned with the number of electrons. We want to know how many electrons are in the volume A times X. This volume here, how many free electrons in there? Before we asked how much water was in there, now we know how many free electrons are in there. So we want to know the free electron density in this pipe or wire. So we give this parameter lowercase n. It's called lowercase n, number of electrons per cubic centimeter, per cubic meter, moles per cubic meter, something like that. The actual number, capital N, in the volume AX is the density, number per volume, times the volume. That's the number. That should make sense. To get the flow rate, we want to know number per time, so we divide both sides by t. The time it takes for the electrons in X to travel that distance, to drain. So we just divide by t, and then we have again this X over t, the same thing that we did with the water. So this is the speed of the electrons that contribute to the current. This is the number of electrons moving past a fixed point per unit of time. So we can stick a guy here, we can say, all right, just count the electrons that go by. Give him a piece of paper and a pencil. Say, go ahead, start counting. Little n, big A, V, electrons per time. We want to get charge per time, so we multiply by the charge per electron. Little q. So here we have it. This is all the charge of the electrons that went by per time, which is the current. And there's our V, and there's our Q. This is coulombs per second. We have to be a little careful with this V here. We talked about V as the speed of the electrons. But the free electrons in the metal are moving at hundreds of meters per second, thousands of meters per second, hundreds of kilometers per second even, the fastest ones. Even when there's no current, right? You have a wire just sitting there, the electrons in there are moving tremendously fast. The average velocity is zero when there's no current flowing. There's the same number of electrons going to the right as there are to the left. And we have to distinguish this. The speed of the current, we call that the drift speed. Electrons are bouncing around at tremendous speeds, but when they head in one direction, when they drift in one direction, we call that the drift speed of the current. It's not the speed of one electron, it's the speed associated with the electric current. And it's the same thing with water molecules. You have water sitting in a pipe, not moving. The individual water molecules are moving at hundreds of miles per hour. They're banging against each other, bouncing around in all directions. The average velocity is zero. There's no net flow, but the water molecules are still moving fast. In air, it's the same thing. If you're sitting in your dorm room, you say, this air's not moving. You say, well, it's moving at, the air molecules are moving at hundreds of miles an hour, but there's no wind, right? All right, so the speed for the electric current is written as this, and we put a little d here to say, you know what, that's the drift speed of the electrons. That's not how fast an individual electron is moving. So to understand how to really wrap our heads around this, let's do a deep dive and consider a 12 gauge wire. The standard wire used in household wiring is 12 gauge. It's got a diameter of a little bit less than 1/10 of an inch, 0.0808 inches, and it's rated for 20 amps. If you put more than 20 amps in it, it's not recommended. The wire's going to get hot. So let's calculate the drift speed of an electron in a 12 gauge copper wire that's carrying the maximum allowed current, 20 amps. So for this, we need the free electron density in copper. This is an intrinsic property of copper. You can look it up. It doesn't matter the size of the wire. You can have a cube of copper sitting there and you say, what's the free electron density? So we need some parameters of copper. Got a density of 8.96 grams per cubic centimeter, an atomic mass of 63.546 grams every mole, and each copper atom contributes 1 electron to the current, 1 free electron. So we have the density divided by the atomic weight, and we get the number of moles per cubic centimeter. About 1/7 of a mole every cubic centimeter. There's 1/7 of a mole of electrons, free electrons in a cubic centimeter of copper. And we can convert that to number, 8.49 times 10 to the 22nd electrons per cubic centimeter. We should probably pause to think about how many this is. This is a lot. 10 to the 22nd every cc. So now we're going to determine the cross-sectional area of the pipe, which is the cross-sectional area of the copper wire. It has a diameter of 0.0808 inches, and we're going to use centimeters here. 0.2052 centimeters for the diameter. We want the radius because we're going to use pi r squared. We divide that by 2. It's about 1 millimeter, 1/10 of a centimeter. So the cross-sectional area is 0.0331 square centimeters, about 1/30th of a square centimeter. So we now have what we need to get the drift speed in a standard 12 gauge copper wire that has a current of 20 amps. There's our equation, and we substitute in the numbers. There's 20 amps, 20 coulombs every second. There's the free electron density in copper. There's the cross-sectional area of our 12 gauge wire, and this is the coulombs per electron. And we can calculate the drift speed. We can see here it's going to be centimeters per second. Coulombs cancel. We have centimeters cubed in the bottom and centimeters squared in the bottom. That ends up being a centimeters in the top. So it's going to be coulombs per second, and the number is 0.0446 0.045 centimeters every second. This is not fast. When the current in a maximum allowed current is flowing in household wiring, the drift speed is only 0.0445 centimeters per second. This is significantly slower than a snail. At this speed, it would take 37 minutes to travel 1 meter. Well, when you switch on the light, it comes on right away. How does this happen? And the answer is that the wire is already full of electrons. It's not correct to think that you flip on the switch and the power supply sends out electrons in an empty pipe. The pipe's already full of electrons. So you're pushing electrons in one end of the pipe, it's already full, and that forces electrons out the other end. It's like a domino effect. It's already jam-packed with electrons. They're so full of electrons, remember it's 8.5 times 10 to the 22nd every cc. So even if you have a small speed, the current is high because there's so many electrons in the wire. So let's imagine a 12-gauge copper wire through which 20 amps is flowing. Again, the current of 20 amps is 1.25 times 10 to the 20th electrons every second. Right? The electronic charge is very small, 1.6 times 10 to the minus 19th coulombs. If we're going to get 20 coulombs every second, we need a lot of electrons. 1.25 times 10 to the 20th every second. So that guy that's sitting there counting the electrons going by, he's counting 1.25 billion every second. So if you can imagine what a billion is, and then you can imagine a billion of those, and then 125 of those. So the question is, how long does a piece of 12-gauge copper wire have to be to contain this many electrons? 1.25 times 10 to the 20th free electrons. It's a great opportunity to think because we already calculated it. How long does a piece of 12-gauge copper wire have to be to contain 1.25 times 10 to the 20th electrons? If you don't know, pause the video and think about it. Spoiler alert. The answer is 0.0445 centimeters because that's the drift speed. This is significantly less than the diameter of the wire. And if we look at a 2-scale view of the 12-gauge copper wire, it looks like this. Here's the diameter of the wire, about 4/5 of an inch. This slice, this tiny slice, 0.04 centimeters, contains 1.25 times 10 to the 20th electrons. So if I push all of the electrons out that are in this tip in 1 second, that's a current of 20 amps. This contains 1.25 times 10 to the 20th free electrons. They have a total charge of 20 coulombs. These will exit in 1 second, producing a current of 20 amps. Let's go back to the previous module and think about this. Capacitors. Here's what we said. We have a circuit like this. We have a capacitor hooked up across a battery, and we said the battery is going to pull electrons from this plate and push them on this plate. Now, with the knowledge that we just gained in this chapter, we can see that that's not exactly right, because these wires are already jam-packed with electrons. They are not empty pipes. So here's what happens when we hook up the battery. This is missing electrons. This has extra electrons. But to get this many electrons, for example, if this is 12 volts and this is a 30 microfarad capacitor, this charge is 360 micro, 10 to the minus 6th coulombs. All right? The charge on the electrons in this tip of the copper wire is 20 coulombs. The charge on a capacitor, a 12-volt capacitor hooked up across a 30 microfarad, 12-volt battery hooked up across a 30 microfarad capacitor, that's 360 microcoulombs. So what the battery did effectively was pull electrons from this teeny tip of the wire push them across and jam them in here. And as soon as the electrons got jammed in this side, it created this tremendous cascade, and the electrons that were right here get pushed onto the capacitor. And of course, that's not exactly right either, because all of these electrons are moving at hundreds and thousands of meters per second, even when there's no current flowing. So who's to say where this electron came from? So this is a good model. This is a good model to think about it. Just realize that the electrons are actually going very fast. That's Module 5, electric current.